Hello everybody, how are you? This is Abhilash here. Welcome to BYJU'S and we are discussing previous year's NEET questions. So this is of course, as I told you, this is part 2 of our interaction. In the part 1, we had already seen half the questions that were from inorganic in NEET 2020. Right. So in this session, we are going to look at the remaining questions from inorganic. And as far as our approach to this session is concerned, in last session also I told you the same. We don't just discuss the question, answer and run through it. We try to look at the background concept involved. We'll try and discuss things as much in clarity and in detail as possible before we go further, right? So yeah, with this, let's start with the questions. Okay, so now let's look at the next question. What does it say? It says, identify the correct statement from the following. So we have to find out the correct statement. This is based on metallurgy. Let's read the options one by one. We'll discuss whatever is there also, right? So A says, blister copper has a blistered appearance due to the evolution of CO2. B says, vapor phase refining is carried out for nickel by Van Arkel method. C option says, pig iron can be molded into variety of shapes. And D option says, wrought iron is the impure iron which has 4% carbon, right? So we need to find out the correct statement. Other three would be obviously wrong statements going forward, right? So in metallurgy, what exactly is metallurgy? Metallurgy is the process, right? It could be starting from the purification of the ore, getting the mineral purification, eventually going all the way to reducing the whatever form, combined form it is, to finally get the metal. That is what you call as your metallurgy. Even after that, we do, once we get that raw metallic form, we can also further refine it, and then also other processes are also there, right? But yeah, point is that broadly we can say that it is the process that I use for the isolation of the metal from its ore, right? So this is broadly metallurgy. And as far as the things that are there in our options are concerned, what do you mean by blister, right? So blister, I'm sure you might have at some point in time had a blister. Let's say that you're cooking a papad or something, and then oil jumps and falls on you, then you end up getting a boil, right? So there is this blister, what we call as a pus and all are there inside, and it bursts and then it feels like a crater out there. That is what you call as a blistering, right? So as far as blister copper is concerned, what is happening here? Copper, right? So when you're looking at cuprous sulfide, Cu2s are starting substance from where we are going to extract copper. What is going to happen? First of all, we have this reaction where we get Cu2O, then Cu2O plus Cu2S reacts, and you end up getting Cu plus sulfur dioxide, right? So yeah, there is blistering that happens. There are evolution of gases that is happening, and the surface of copper will not be smooth and even and all, right? So there will be this crater kind of feeling that you are going to see there. So yeah, blister is a fluid filled bubble people get when it could be also because of getting rubbing, skin gets scratched and all of these. But yeah, burns and all, oil boiling, oil falls on your skin, all of these could happen. But yeah, going forward, saltified copper that you obtain after metallurgy, right, before we go on to further refining or purifying it and all, it's what you call as blistered copper. It has this blistered appearance due to the evolution of sulfur dioxide. The question said it is because of the evolution of CO2. So it's a very nice question, tricky question. It has all the statements that look partially right and it is partially wrong as well, right? So here there is blistering happening, there is gas evolving, but it's not CO2, it's sulfur dioxide, right? So it is with the evolution of sulfur dioxide that blistering happens, right? So yeah, reactions I have already written, but yeah, let me just repeat it nonetheless. Cu2S plus O2 giving you, right? So first of all, you're going to get Cu2O and SO2, right? How do you balance this? Let me write 2 and 2 CO2 and 2 SO2 and 3 O2, right? And after that, CO2O can also react with Cu2S, and then you end up getting copper and sulfur dioxide. So let me write 2 here, and 4 plus 2, 6 copper, right? So yeah, these are the two valence reactions, and this evolved sulfur dioxide is what causes this blistering. It is not carbon dioxide, so the given statement was wrong, right? Now the second statement was related to nickel and the vapor refining, right? So what do you mean by vapor refining? The idea is that there are these compounds of some of these metals which are having covalent character, because of which they can easily vaporize, right? So they can be converted into vapor phase very easily. So there are broadly two types of vapor refining processes that we come across, right? So yeah, what is written in the method, metal is converted to its volatile compound and it is collected separately. So the metal is sitting there. Metal is there with other impure metals as well. So I want to selectively take out this metal. What do? I facilitate a reaction where this metal can form some kind of gaseous ion, and then I can pump it outside. The other metals, the impure metals, are all lying around there inside, and I can take this gas outside and then do some chemical reaction again to it and take out the metal from the substance. This is the idea, right? So here what do we have? Broadly, this vapor refining process can be broadly divided into two. One is called Mons process, which is specifically used for nickel, and the other is called Van Arkel process, which is primarily used for zirconium and titanium, right? So so let's look at this Mons process. The question said, the option said vapor refining of nickel is done through Van Arkel process. So it was a wrong statement. That's why I said tricky, nice question. Everything looks like okay if you are partially sitting there remembering that okay, I think nickel had vapor refining, but I'm not sure if it's Van Arkel. Maybe it's called Van Arkel, and then you end up clicking that this is the right answer. You will go wrong, right? So yeah, nickel is heated in a stream of carbon monoxide, forming this volatile complex, which is your nickel tetracarbonyl, right? So what is happening is that nickel, not very high temperatures and all are needed. 50-60 degrees will be sufficient. Nickel plus 4 carbon monoxide at 50-60 degrees, it gets converted into NiCO4, nickel tetracarbonyl, which is volatile in the sense that it will be in gas phase and I can easily take out. So you understand that the other metals other than nickel is not having this reaction. They are still lying down where they were, but my nickel carbonyl is in gas phase. I can take it outside and I can re-extract this nickel at a high temperature, right? So they are subjected to higher temperature so that the decomposition takes place. So NiCO4, if I take nickel tetracarbonyl at let's say 200-250 degrees, right? 250 degrees Celsius, what we end up getting is nickel once again, and the carbon monoxide is evolved. So I can take the carbon monoxide again and continue with the process. This process specifically is what you call as your Mons process for refining of nickel. This is not Van Arkel process. So what is this Van Arkel process? In Van Arkel process, the impurities are basically removed by the same methodology. The idea is that volatile, covalent character, high covalent character metal substance, metal compound is made, and then it is taken outside and the metal is re-extracted from it. Like for example here, zirconium and titanium are heated with iodine, right? So it first gets converted into ZrI4, for example, with zirconium, and then with tungsten at a very high temperature, around 1700 Kelvin, 1500 degrees, roughly somewhere around that, you should be able to get back your zirconium, right? So what is happening here? Let's look at the process. So crude metal zirconium, crude means it has impurities also, okay? So crude metal zirconium is heated in evacuated vessel with iodine vapors. So zirconium plus 2 iodine in gas phase, and you are getting ZrI4, zirconium tetraiodide. This is basically our volatile substance that is produced, right? Now this zirconium can be re-extracted. You use a tungsten filament, passage of electricity can cause very high temperatures, right? Tungsten, highest melting point and all, one of the highest melting point metals, right? So we take it to around 1700 degrees, a tungsten filament, and on top of that this zirconium will be deposited because of breaking down of this zirconium iodide, right? So ZrI4 breaks down into zirconium plus 2I2 once again, right? So what are we doing? The metal iodide is decomposed on a tungsten filament, W, wolframite, right? Tungsten at around 1700 Kelvin, and the pure metal is deposited on the filament. This is what you call as Van Arkel process. This is used for zirconium and titanium, not for nickel, as what was said in the question, right? Now going forward, as far as iron metallurgy extraction is concerned, one of the first forms of iron, impure forms of iron that we get is called pig iron, right? So it is relatively softer, high percentage of carbon, 4-5% carbon, and other impurities are also there, sulfur, phosphorus, silicon, manganese, and all of these are there, and it can be easily molded into shape, right? It's not a very hard metallic, very strong kind of a substance. Pig iron can be easily molded into different shapes. Wrought iron is also something that was there in D option, right? So wrought iron is a very pure form of iron, right? So it has way less percentage of carbon, 0.05% carbon, and it is the purest commercial form of iron that you can think of, pure iron that you can think of, with very low carbon. In order to make stainless steel and all, you do other things, you add other carbon and other elements and all, that's a different story. But yeah, wrought iron is not your impure form of iron as what was suggested in the option. It is one of the purest forms with very low percentage of carbon. The option said around 4% carbon in wrought iron. No, that is there in pig iron, right? So you might have also heard about cast iron. So it's not there in the question. Let me briefly speak about that also. So as far as cast iron is concerned, cast iron is much more harder and brittle, right? So it's much more stronger. It can't be obviously then molded into different shapes. It is prepared by using pig iron plus scrap iron. What do you mean by scrap iron? Scrap dealer, you might have heard of, right? So useless metals, right? Metal that has served its purpose in its first life, and now it can be used to produce what you call as your cast iron. Pig iron plus scrap iron and heated in a blast, right? So hot air blast should be there along with coke, of course. You heat it, and this cast iron has slightly less percentage of carbon compared to your pig iron. So around 3% is what is written here. It is much more harder and brittle. It cannot be molded into shapes, right? So that is reserved for pig iron. So of course you might be remembering, yeah. So looking at the options, A option said, that's why I said this is a good question. All the options look as if they could be right? But they are not. So blister copper has blistered appearance due to the evolution of CO2, wrong, right? Vapor phase refining is carried out for nickel by using Van Arkel method, no. If you said Mons process, yes. Pig iron can be molded into different variety of shapes, true. This is our answer. And wrought iron is impure iron, no. It is one of the purest form with very low carbon percent, 0.05%. So our correct answer is, of course, what? C option. Okay, so now let's look at the next question. Okay, this question says identify the incorrect statement, right? So we are given 4 statements and we have to identify the incorrect one. Let's read out the options one by one first. The transition metals and their compounds are known for their catalytic activity due to their ability to adopt multiple oxidation states and to form complexes. Pretty much a standard statement. I'm sure you have heard even in NCERT, right? The interstitial compounds are those that are formed when small atoms like H, C or N are trapped inside the crystal lattices of metals. Okay. Next statement says the oxidation states of chromium in CrO4 chromate and Cr2O72 dichromate are not the same. This is what it says. And the last option says Cr2 plus D4 configuration is a stronger reducing agent than Fe2 plus D6 in water, right? So let's see. Let's look at the statements one by one. The first statement was about transition metals and their ability to act like catalysts and all because of the presence of variable valencies and what you call as your MTD orbitals and all, right? So this is pretty much a standard statement, right? So I'm sure you have come across this, that a lot of transition metals and their compounds and all of these are used as common catalysts because of the fact that they can show variable valencies. They can temporarily accommodate accommodate electrons and all. That is the reason why this happens. Transition element. What exactly is a transition element in the first place? The one which has incompletely filled d electrons, d orbitals in its ground state or in one of its oxidation states, right? So yeah, it should have incomplete d orbitals. There should be like 1 electron, 2 electrons, something like this in one of either in its atomic form or in its one of its stable oxidation states. If this is seen, then we say that okay, it is a transition metal. So by this definition, for example, zinc is not a transition metal. Why? Because zinc metallic form also it is 4:3d10 fully filled, and in its stable oxidation state +2, Zn2 plus also has 3d10 which is fully filled. So it's not a transition metal, right? Okay, anyways, that was an tidbit of information extra. Let's go further. So yeah, the transition metals and their compounds. I mean, compounds don't show variable oxidation states. Transition metal shows variable oxidation states, and they have compounds in which the metal has multiple oxidation states and all. So yeah, this is the reason. Plus the fact that they have the immediately inner D shell, right? D subshell of the inner shell, just inner, right? So outermost shell, for example, in your 3D series elements is fourth shell, 4s, right? And your inner shell, third shell, has 3D, which is something that gets involved as far as bonding is concerned, because of the fact that 3D has like higher energy compared to 4s, but it is still like an inner shell and all, right? So the influence, it is the you can say it is in the sphere of influence of the nucleus. The nucleus will be able to attract the electron clouds that are in that region. So this is the reason why transition metals can like kind of hold on to lone pairs and all if there are empty orbitals, right? So yeah, many catalysts I'm pretty sure you have come across where you have transition metal compounds, right? Like for example, the Ziegler-Natta catalyst is something that is used, for polymerization and all, right? So it's a titanium halide, titanium chloride plus ET3, Al2ET3, right? So if you tetraethyl aluminum, this particular one combination is what you call as your Ziegler-Natta catalyst. Natta had changed the Ziegler catalyst. Originally it was just TiCl4 based, and Natta modified the catalyst to include the organometallic and all, and it changed its activity, right? So it improved its efficiency. So that is also something where you see that as far as titanium is concerned, because of the fact that it can accommodate more than one different electron clouds around it and all, groups around it and all. That is the reason why this particular, once you go into the mechanism of how Ziegler-Natta catalyst works, there you will understand this better, that this fact that it can form complexes is something that helps it become this catalyst in this particular case, right? So these metals also catalyze reactions by providing suitable reaction surface, right? So you have come across this question even in mole concept in physical and all, where you speak about number of surface sites available, right? So these metals, when they are like providing surface size for adsorption, physical adsorption of different gases and all, they facilitate easier reaction, right? So they hold things in place so that the collision between particles are more effective and all. Example would be like catalytic hydrogenation with the help of nickel, where hydrogen gets adsorbed on the surface of nickel and it acts like a catalyst in that case, right? Next option was speaking about what you call as interstitial compounds. What are interstitial compounds? When you have these metals, you have heard that they crystallize into different lattices, right? So metal atoms, based on their, when they are in pure metallic form, they have these metal crystal lattices that are formed. Now, obviously, whenever you have like these lattices, there are going to be void spaces, right? So nothing is like 100% efficient packing. Atoms are not like bricks that you can, pack all of them together and all. No, right? So they are like spherical, more or less spherical in nature. So whenever you pack them up, there is always going to be vacancies within the crystal lattice, right? So when you have these very small atoms like hydrogen, nitrogen and carbon, I guess, or something was written here, boron and all of these very tiny atoms that are there, they can get trapped within your metal, right? So if they are trapped within the metal crystal, then such kind of substances are what you call as your interstitial compounds, right? So compounds which are formed when small atoms like hydrogen, carbon, nitrogen, boron, etc. are trapped inside the crystal lattice of the metal. Obviously it shouldn't be metallic. You can understand metal plus metal kind of situation is not what we are looking at. Primarily we come across this very tiny non-metallic atoms getting trapped within this. That is what you call as interstitial compounds. The next option was about the oxidation state of chromium, right? In chromate and dichromate, it said that they are not the same, right? Now, what do you mean by oxidation state? As we have already seen in our previous part as well, that as far as oxidation state is concerned, you can think of it as the charge that will be there on an atom if we manage to break down all the bonds around that atom and redistribute electrons according to electronegativity. So when I'm looking at CrO4 minus chromate ion that is given here, if I manage to break down all the bonds and redistribute electrons on the basis of electronegativity, the charge that I get is what I'll call as the oxidation state. So obviously, oxygen being way more electronegative than chromium, what we will see is that oxygen will get both the electrons if we manage to break the bonds. So obviously these will also go with oxygen. All of these are going to go with oxygen. And we can say that, okay, so all the 6 electrons are lost by chromium if I'm breaking the bonds. So the charge has to be plus 6. Now, obviously, there is other way to calculate this as well, right? So what we say, like for example, if you have something like CO2, or let's say, in fact, for that matter, CO3 2 minus, right? So when we look at the individual oxidation states on all the atoms and add all of them up, what we end up getting is the net charge on the species, right? Like minus 2, minus 2, minus 2 and plus 4. The sum of oxidation states is equal to minus 2, which is the charge on our item in the first place. CO3 2 minus charge. So this is another logic that we can use to calculate as well. What we will say is, okay, let's say X is the oxidation state of chromium. So X plus, there are 4 oxygen atoms, all of them in minus 2. So 4 into minus 2 should be equal to minus 2, right? Or X minus 8 is equal to minus 2, or X is equal to 8 minus 2, or you can say X is equal to plus 6, which is the oxidation state of chromium. Similarly, in dichromate, if I try to calculate, we can see that, okay, this chromium is also going to lose 6 electrons because all of them are attached to oxygen atoms and oxygen is more electronegative, right? So what we'll see is that even this chromium is in plus 6. Exactly identical is the situation here as well. You can see 6 electrons all shared with oxygen atom, which is way more second most electronegative, right? So you will end up getting a plus 6 charge even here. So this was the wrong statement, right? So we can use the algebraic method also. We can write 2x plus 4 into 7 into minus 2, right? So 2x plus minus 14 is equal to minus 2, or you can say that 2x minus 14 is equal to minus 2, which means that 2x is equal to 14 minus 2, 12, or you can say x is equal to plus 6, which is same as what was there in chromate. So this is our wrong statement. Going further, we are speaking about reducing power next, right? So we had to see the natural observation that is there, that our Cr2 plus is a better reducing agent than Fe2 plus, right? So one way, obvious way to handle this is to look at the reduction potential, standard reduction potential or standard oxidation potential, to look at the feasibility of oxidation or reduction, and accordingly we could decide which is the stronger reducing agent, right? So when I'm looking at the standard reduction potential of Cr3 plus to Cr2 plus, we get a negative potential, right? What do you mean by negative potential? Whenever your E0 value is turning out to be negative, what this means is that this is not feasible, right? So we can also go via Gibbs energy angle, that standard Gibbs energy change will be equal to minus NF E0, which means that if E0 is negative, standard Gibbs energy change is positive, which means under standard conditions this is not a feasible reaction to take place, which means that this is not a process that will happen spontaneously, which means if I reverse the reaction, we know the potential changes, right? So if I look at E0 of Cr2 plus to Cr3 plus, this is what? Oxidation potential, standard oxidation potential, it is turning out to be plus 0.41, right? Whenever you look at potential, think of it as ability, right? So ability of a reaction to happen, you are writing it as positive 0.41. This will happen. This is a feasible process, which means Cr2 plus will be happy to give out electron. The reason behind this is obviously electronic configuration and their stabilities and all. That's a different story. But yeah, point is that when we are looking at reduction of Cr2 plus oxidation of Cr2 plus to Cr3 plus, we are seeing that there is a potential positive ability of this to happen. If I look at E naught of Fe2 plus to 3 plus, which means that the oxidation of Fe2 plus to Fe3 plus standard conditions, we are seeing minus 0.77, which means if I have 1 molar Fe2 plus 1 molar Fe3 plus in one solution, Fe2 plus will not go to Fe3 plus because we are seeing a negative potential here. Rather, Fe3 plus would be happy to go to Fe2 plus. Again, the reason behind this is because of what you call as stabilization and all. Obviously, you can understand that if you look at Cr2 plus, for example, Cr2 plus has what configuration? Chromium is 24, so Cr2 plus will have 22, and we end up getting what electronic configuration? We are getting yeah, so argon 4s1 3d5 is what chromium was originally, but chromium 2 plus will be argon 3d4, right? So as far as electronic configuration in aqueous solution is concerned, this is 3d4, which will have what you call as electrons in your T2g orbitals and Eg orbital. One orbital will have one electron. You have to understand that the stabilization and all decides the when we speak about individual, let's say for example Fe2 plus and Fe3 plus ions, Fe2 plus configuration is Ar 4s2 3d6 was the original. This is 4s 4s0 3d6, and Fe3 plus has a configuration of Ar 3d5. So just as an independent standalone ion, this would have been more stable, but what we see is that in aqueous solution your Fe2 plus is more stable. What we will see is that 3 plus to 2 plus conversion is pretty obvious. You can see here reduction has a positive potential, which means that this is a feasible process, which means the reverse process is not that feasible. So just based on the reduction potential value, we can see that Cr2 plus to Cr3 plus conversion is easier, which means it is a better reducing agent because it is easily getting oxidized, right? So yeah, the statement that was given to us is also pretty much true, right? So looking at so the theory behind it is also given here. Lower the value of reduction potential, higher will be the reducing power of that ion, right? So yeah, obviously Cr2 plus is your stronger reducing agent compared to Fe2 plus in water at least, right? Yeah, so we were here. What were we doing here? We were looking for the what you call as your incorrect statement, right? So the transition metals and their compounds are known for their catalytic activity due to ability to form multiple oxidation states and form complexes. This is pretty much true. Interstitial compounds are formed because of small atoms being trapped inside your crystal lattice. This is also true. Oxidation state of chromium in chromate and dichromate are not the same. This was wrong. We know they are both in +6 state. And your Cr2 plus is better reducing agent. This is true than Fe2 plus. So our correct answer is of course C option. Okay, let's look at the next question now after this very interesting question that we had. The question says, which of the following set of molecules will have zero dipole moment? Simple question, we will rush through this, right? So what do you mean by dipole moment? Whenever there is a bond, because of the difference in electronegativities, we see what you call as a partial ionic character developing in a covalent bond. There is what you call as polarization of electron cloud that is there. And as far as overall molecule is concerned, a molecule with a lot of individual polar bonds, this kind of a bond is what you call as a polar bond. If the net vector sum of all of these individual dipole moments, if it turns out to be zero, the molecule is said to be non-polar. If the net vector sum is there, a non-zero value is there, then we say that the molecule overall is polar, right? So let's quickly see the options given: boron trifluoride, hydrogen fluoride, carbon dioxide, 1,3-dichlorobenzene, 1,4-dichlorobenzene also I can see somewhere down the line, nitrogen trifluoride. Okay, so we'll have to look at all of these options one by one, right? So I've added the images of all of these so that we can go quickly through this. So yeah, what is dipole moment? As I told you, charge into separation of charges, the magnitude mu is equal to d into q, and as far as individual bonds are concerned, because of electronegativity difference, there is a dipole. It's a vector. In chemistry we draw it showing the direction of movement of electron, positive to negative. Physics, it is reverse. And as far as net vector sum is concerned, if it is 0, we call the substance, the compound as a non-polar one, right? So so it arises in a system. So dipole moment arises in a system where there is a separation of charge. This is because of electronegativity difference. This is due to electronegativity difference between the bonded atoms, right? So let's look at the options one by one. In option A, we had BF3, HF, etc. BF3, even though individually they are polar bonds, right? So there will be a delta minus on fluorine and delta positive on boron. Individually the bonds are polar, but they are all at 120 degrees to each other, and the net, they are exactly identical, right? All the bond dipoles are exactly identical. The net vector sum that we end up getting will be 0, right? But in HF, obviously there is a delta plus and delta minus, so this is a polar molecule, right? So we are looking at the option where all of them are non-polar. So A option can I discard just because of this so just because of this HF, I can say that option A can't be the correct answer, right? So already we got it. And as far as benzene is concerned, right? So in benzene, in fact, dichlorobenzene, 1,3-dichlorobenzene is what we have. So this is 1, 2, 3, 1,3-dichlorobenzene. As far as benzene is concerned, original benzene was a non-polar molecule. The individual bonds are also not really considered polar. Carbon-hydrogen bond, for all practical purposes, is considered to be non-polar. There is a small electronegativity difference, of course, we have studied about this, but it's not a very strongly polar bond, right? But yeah, overall, because of the symmetry that is there in original benzene that we have, you can say that benzene had 0, right? Benzene had 0 dipole moment. But now that we have a chlorine here, and chlorine is more electronegative, there is going to be one dipole like this, and there is going to be another dipole like this. Obviously, they are not going to cancel each other out. We will get a net vector sum. We will get something like this, right? Whatever. There is going to be a value. It is not going to be 0. So again, this is also wrong. So option A, I have discarded. Carbon dioxide will have a net 0, obviously. So because both of these are exactly identical, we can say that this is non-polar, right? Going forward, in option B, we had NF3 as the first one. NF3, again, same story. Individual bonds are all polar. Lone pair is also, what has happened to lone pair? Lone pair was supposed to be entirely around the single nucleus, but after bond formation, it's like thrown away. Not exactly thrown away from the atom, but it feels as if it is getting thrown away a bit. This is the direction that we give for your lone pair, right? So lone pair dipole, you give it a direction like this. The individual bond dipoles are all going to be like this, right? Obviously, the net vector sum will be there. This is not going to be exactly 0. So this is also a non-polar substance, right? This is also a polar molecule, right? So individual bonds are polar. Overall molecule is also polar. BF2, we will end up getting a net 0. Right, because they are exactly identical, this will turn out to be 0. In H2O, obviously, we know H2O is polar, right? H2O is the, polar solvent. You have heard this, right? One of the best solvents, right? So H2O, of course, is polar. 1,3-dichlorobenzene we had already seen to be polar. C option, let's see. BF3, again, same story. The 3 vectors will cancel each other out, so this will turn out to be 0. Here also, the 2 vectors will cancel each other out, so this will also turn out to be 0. Next option, CO2, same story. Wow, all of them are turning out to be 0 so far, so this is also 0. And the last one is 1,4-dichloro. Here, the 2 chlorine are exactly diametrically opposite to each other, right? So here they can cancel each other out, right? One thing you have to remember is when you have your 2OH instead of 2Cl. That is a very interesting question. I'm sure you remember this. Just check it out, okay? If you already know, comment in the link, right? So when you have 2OH instead of 2Cl, will it still have 0? I want you to comment in the box, right? So yeah, so here you will end up getting a 0 net dipole. So obviously option C is our correct answer, right? So going forward, when I'm looking at option D, again, this is a non-zero. We had already seen this, right? So no, in fact, this is NH3. NH3 will see the 3 bonds and the lone pair adding up, right? So these are the 3 individual dipole moments. They will add up. and the lone pair dipole moment is also in this direction. So overall we get a much higher dipole moment than your NF3. Standard question, I'm sure you have studied in this in school, right? So this one turns out to be 0. Of course, BeF2, H2O is obviously polar and this is non-polar, but yeah, we wanted all the options to be like 0, right? So in this question, which set of molecules will have 0 dipole moment is what was asked, right? So which was our option? Our option was of course C option, BF3, BeCl2, CO2 and 1,4-dichlorobenzene, option C. Okay, now let's continue to the next question. Right? So what is this question saying? This is a very simple question, one of the simplest questions. I'm sure you would also start laughing looking at this question, right? So match the following oxide and nature. First is carbon monoxide, then we have BaO, Al2O3 and Cl2O7. Nature wise we have to match it to basic, neutral, acidic or amphoteric. Pretty simple as it gets, right? So yeah, so the option, which out of these options is correct, we have to match them and find the correct answer. We'll see, we'll come back to this, right? So yeah, so what exactly is this? We are looking at nature of oxides, which is a part of periodic properties if you want to look at it that way. As far as nature of oxides is concerned, you can remember this very easily in the periodic table. You know, left side you have all your metals, you have your non-metals on this side, right, in a small triangular kind of area. So you have your non-metals on the right side, metals on the left side. Metallic oxides are basic oxides, you know, right? So sodium hydroxide, barium hydroxide, calcium hydroxide. So you will be having basic oxides on this side. You will be having non-metallic oxides like carbon dioxide forms carbonic acid, sulfur dioxide forms sulfurous acid, all of these, right? So you know that non-metallic oxides are acidic in nature, right? So left to right, nature of oxide goes from basic to acidic in a periodic table, right? So now with this idea, right, obviously now you can understand that some of these substances can have intermediate properties also, right? So if you have some elements which are lying in this border region roughly, I mean not always, there is like influence of oxidation state and also I'm pretty sure you have heard of this. The point is that some of these oxides do have this tendency that it can react with both acids as well as bases, which we call as amphoteric. And then we have these oxides which we call as neutral oxides, which doesn't give you an acid or a base in solution, right? So yeah, let's look at the options and let's understand. Metallic oxides, basic oxides, non-metallic oxides, acidic oxides. There are some oxides which shows these both of these properties, some oxides which don't react at all, right? So yeah, so as far as standard example of a neutral oxide is concerned, that is your carbon monoxide. Carbon monoxide doesn't give you an acidic solution or basic solution in water. So Al2O3 is an amphoteric oxide. I'm sure you have heard of NaAlO2 as well as AlCl3, right? So AlOH thrice can basically Al2O3 can react with NaOH as well as HCl, right? So going forward, here we had like carbon monoxide, which is a non-metallic oxide, which is a neutral oxide. It doesn't dissolve and all like others. BaO, basic your barium oxide, right? Which family is this? Calcium family, right? Beryllium, calcium, beryllium, magnesium, calcium, strontium, barium, radium, right? So barium oxide is strongly basic as well, right? Very, in fact, within your strong bases, like this is definitely there, right? So your NaOH, KOH, RbOH, CSOH are strong bases. Barium hydroxide is also a strong base. Strontium hydroxide is also a decently strong base, right? Other hydroxides are normally weak bases. Anyways, that's a part of ionic equilibrium. But yeah, continuing. So barium oxide is metallic oxide, which is a basic oxide. Aluminium oxide is metallic oxide, of course, but it is an amphoteric oxide which can react with both acids and bases. Cl2O7 is the anhydride of your HClO4, right? So which is your perchloric acid, a very strong acid indeed, and this is an acidic oxide as well, right? So non-metallic oxide, you can see it is a non-metallic oxide, that too in its highest oxidation state, fluorine +7. So it is going to be acidic in nature, right? So matching wise, what do you see here? Carbon monoxide A should come to 2 neutral, barium hydroxide should go to 1, which is the basic, Al2O3 should come to amphoteric, and Cl2O7 should come to acidic. So A2B1 C4D3, this is what we are looking for, right? Yeah, so looking at the options, what do we see here? So we have A2B1 C4D3. Oh wow, brilliant. So A itself is our right answer that we were looking for. Very simple question. To be honest, such a simple question is not probably expected anywhere, right? Anyways, so A is the correct answer to our question. Let's go to the next question now. Let's see, what does the question say? It says identify the incorrect match, right? So this is obviously, I don't expect this question to be something which is very interesting. This is something that is purely information based, right? So what is given here is like IUPAC names, symbol wise IUPAC declared names, and from there the IUPAC current official name is asked. This is purely information based. So I have added all of these 100 plus elements, Z greater than 100 elements, where we use this nil, un and all of these. I have added as many names as possible out here in the solution here, so that you can try to remember them. Again, if you ask me to remember it, I won't. I'll probably just leave this question, but yeah, I mean, up to you. If you want to remember the names, some like around 100 plus, you have like what, 10-15 elements at max, so who have this IUPAC official names as well. IUPAC rule based name is a different story. IUPAC official name associated with some scientist or some place and all of these, they are also there. If you remember, good for you. Would I ask you to compulsorily remember this? No, of course not. Don't overtax yourself. If you don't want to remember it, don't, right? Yeah, so let's read here what we have. I at least will brush up on this part. So let's see. So what is given to us, we have to find the incorrect match. Okay, so in this list, what is being said is that some of the names are true, right? So Unnil anium mendelevium, unnil trium laurentium, unnil hexium is given as seborgium, and your anium is given to us as darmstadtium, right? So we have to see which is not right, right? So 3 of them are right, 1 is wrong, right? So obviously the IUPAC system behind this is something that we have to know, right? So what is the idea? When your atomic number is greater than 100, there are going to be these 3 numbers. These 3 numbers are replaced by different symbols and sounds, right? So 1 is replaced, for example, by un, right? And you have, let's say, for example, 3, then this is tri, and then you have, let's say, for example, 6, so it will become hex, right? So untrihexium, if there is an atomic number 136 element, this will be the IUPAC name. Official name might be added to some scientists later on at a later stage. That is not our concern, right? So yeah, so the roots are put together. Digits from 0 to 9 have like replacements, and for example 104 is unnil quadium, right? So let's see, I'm pretty sure you know all of these, but yeah, 0 is replaced by nil, 1 by un, 2 by bi, 3 by tri, quad is for 4, of course, pent is for 5, hex for 6, septoct n, right? And you just like substitute these symbols instead of the numbers. You should be able to get the IUPAC name, and the official name is obviously something you can't just get it randomly from anywhere. So I put all of the names here. Remember as much as you can. If you do end up getting a question from this, who knows? But yeah, because it was there in 2020, I don't expect it to be there in 2021, to be honest. Symbols, abbreviations are also there. N, the first alphabet, right? So N, U, B, T from tri, quad Q, pent P, hex H, sept S, oct O, and N is E, right? So none of the alphabets are repeated also. You might have noticed this. So yeah, some of the names I have added here. Again, do I remember all of these? I don't. To be honest, I don't. Do you have to remember all of these? Up to you, right? Okay, so 101, what will it be? Aniline, right? So aniline, it is mendelevium, which is given in our list, right? So what were the, let me just quickly see what were the elements given to us, right? So the numbers, at least if I remember all of them, it will be nice. So we had aniline, so 101, anilrium 103, anyl hexium 106, and anium would mean 111, right? So mendelevium, lawrencium, seaborgium, and darmstadtium, right? These are the names that are given. Let's see what the so 101 is mendelevium, which is true. 103 was also there in our list, which is given to us as lawrencium, which is also true. Then we had 106, which is given to us as seaborgium, which is also true. And then we had 111, which is obviously on the next page, right? So mendelevium, nobelium, lawrencium, rutherfordium, you can see these are all like tributes mostly, right? Dubnium, seaborgium, borium, Bohr, all of these are like very famous scientists, right? So hassium, then you have your meitnerium, and then 110 annilium, right? Yeah, 110 is darmstadtium, right? We were told that 111 is darmstadtium, 111 is actually röntgenium, right? Röntgen, X-ray, right? So röntgenium is basically your 111, so this is obviously what is wrongly matched, right? So let's look at the options. D is wrong, basically. Others were right? So we had our mendelevium, we had our lawrencium and seaborgium, these were right. Only darmstadtium, röntgenium, these names have been changed, right? So 101 is mendelevium, 103 is lawrencium, 106 is seaborgium, 111 should have been röntgenium, right? Röntgenium should have been the name, but darmstadtium was given to us, which was 110, so that was the one that was wrongly matched, right? So the question was asking us, can you look at the IUPAC names and the official names and guess which one is wrongly marked? So looking at these, I can see that the obvious one that is wrongly marked is the anium one, which is called darmstadtium. It should have been röntgenium, right? So D4 is the one that is wrongly matched, which means C is the correct answer to our question. Okay, so let's continue. So let's go to the next question. Let's read the question. It says, identify a molecule which does not exist. Simple question based on MOT. Something that when you look at it, I'm sure you will get the answer straight off, but let's look at the options. Li2, C2, O2 and He2, right? I'm pretty sure you already know the answer, but yeah, let's see. So what is, you can see that all of these were homonuclear diatomic molecules, right? So homonuclear means that both the atoms are the same and you have diatomic molecules that we are speaking about, right? So Li2, oh, lithium metal diatomic covalent. Yes, it does happen, right? So these diatomic molecules, we look at them on the basis of MOT, right? Molecular orbital theory. We try to look at the total number of electrons. We say that metal, why metal? These atoms, they had these atomic orbitals when they were alone and separated and all, but now that they are close to each other, more than one nuclei, more than one attracting centers are there in these molecules, and atomic orbitals lose their relevance. What we have now are what you call as molecular orbitals. We speak of linear combination of atomic orbitals. We speak of constructive and destructive interference between these electron waves, right? So we speak about what you call as a molecular orbital, right? A bonding molecular orbital. When two atomic orbitals combine, we speak of a bonding molecular orbital and anti-bonding molecular orbital that are formed. Anti-bonding molecular orbital having a higher energy, bonding molecular orbital having a lower energy, and so on, right? So I'm sure you remember in MOT, for a number of electrons less than 14 we have another order, for number of electrons greater than 14 we have another order. Let's look at the molecules that are given to us. We'll write down their electronic configuration and we will calculate their bond orders, right? So why? Because that is the official way to determine if a molecule will exist or not. If there is a positive value for bond order, then we can say that the molecule or the species, whatever it is, will be able to exist. If it is having zero bond order or negative bond order, we say that that substance cannot exist. What is this bond order in the first place? This bond order is basically equal to bonding electrons minus anti-bonding electrons divided by 2. Total number of bonding electrons once you have written down the configuration minus total number of anti-bonding electrons once you have written, once that electronic configuration written. B minus A by 2 is going to give us our bond order. If it is not 0 or negative, we can say that the molecule will exist, right? So 1 to 14 electron system, right? So you have this order sigma 1s, sigma star 1s. From 1s and 1s we have sigma 1s, which is your bonding molecular orbital, which is at a lower energy, and sigma star 1s, which is your higher energy molecular orbital, which does not favor bonding. So sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This much is same for everybody. After this, how I remember this is 2 1 2 1. Right? The trick to remember is less than 14, 2 1 2 1, greater than 14, 1 2 2 1. Right? 2 1 2 1, 1 2 2 1 2 1 and 1 2 2 1. What do you mean by 2 1 2 1? This is basically my 2, this is basically my 1, this is basically my 2, and this is basically my 1. Right? So pi 2px, pi 2py, sigma 2pz, sigma 2p. Sigma is normally supposed to have lower energy than pi, but yeah, here it so happens that there is this concept called sp mixing, because of which we see that pi 2px, pi 2py has a lower energy compared to your sigma 2pz. Then after that sigma 2pz, after that you have your pi star 2px, pi star 2py, and then last is sigma star 2pz. This is the generic order that you would expect in a homonuclear diatomic molecule with number of electrons less than 14. To be honest, let's not go by number of electrons. Let's say that the nuclei have 7 or less, right? Nitrogen or lower elements, basically. Okay, so disclaimer is given. Z-axis is considered as the internuclear axis. This is a common case scenario. Sigma we assume along Z-axis, pi will be along X and Y axis, right? Okay, going forward. So this is for less than 14. For greater than 14, as I was telling you, 1 2 2 1. What do I mean? This is also written as K, K dash, L, L dash. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. After that, you have 1, 2, 2, 1. This is our 1 2 2 1, right? So 2 1 2 1 less than 14, 1 2 2 1 greater than 14. This is how we can remember this. This is the energy order for your orbitals. Mind you, this is not obtained from something like N plus rule or anything. This is experimentally determined. For homonuclear molecules, this order is pretty consistent. There is at least something we can write. But if you have heteronuclear molecules where the atoms that are undergoing mixing, right? So bond formation have like drastically different energy levels and all, then molecular orbital theory is not, at least at our level, useful there. Of course, molecular orbital theory is the ultimate thing, but yeah, experimentally you will have to find out energies of different orbitals and their order and all. There is no definite order that you can speak of in heteronuclear molecules. Just keep this in mind, right? Primarily, homonuclear molecules is what we see. Cool. So going forward, what all molecules did we have? So yeah, I have already told you about bond order. Bond order helps us in finding out whether a molecule will exist or not. It is B minus A by 2, bonding electrons minus antibonding electrons by 2. If it turns out to be negative or 0, we say it won't exist, molecule won't exist, right? So bond order is related to bond length as well, stability as well as the existence of molecule. Bond order, if it is high, bond length will be low, right? So in a very simple way of thinking, you can say bond order is number of bonds. So bond order is 1, single bond. Bond order is 2, double bond. Bond order is 3, triple bond. So more the number of bonds, obviously bond length will get shorter, right? So bond length is inversely related to bond order. Stability is directly proportional to bond order. Single bond, less stable. Double bond, more stable. Triple bond, even more stable. So bond order is directly proportional to stability as well, or stability is directly proportional to bond order. Existence of molecule, I have already told you, can be determined using bond order. So what is given to us here, different molecules are there. We will do this for all of them. Half of NB minus half of Na, and if it turns out to be 0 or negative, we say molecule won't exist, right? So 0 or negative, we say that the molecule does not exist. If it is positive, we say that okay, molecule can exist, right? So let's see, Li2, 6 electrons in all, less than 14, so you have your 2 1 2 1 order, but yeah, whatever. So sigma 1s2, sigma star 1s2, sigma 2s2, 6 electrons are gone. So number of bonding electrons is 4 and debonding electrons is 2. So 4 minus 2 by 2 equal to 1, which means Li, single bond Li, right? So lithium is a metal. Why is it forming covalent bond? Yes, in vapor phase, metals also exist in the form of covalent diatomic molecules many times, right? So for example, Li2, right? So bond order, what are we saying? Okay, so we have already calculated this, half of 4 minus half of 2, right? I mean half of 4 minus 2, but yeah, whatever. So yeah, since there are two separate brackets, I'm writing like this. So 2 minus 1 equal to 1. So yes, Li2 does exist. C2 has 12 electrons. Very interesting molecule as well. Before forming by bond sigma bonds, it has 2 pi bonds. So 2 carbon atoms in vapor phase, C2 molecule, right, in vapor phase exists with 2 pi bonds and no sigma bonds. Very interesting, right? Sigma 1s2, sigma star 1s2, they cancel each other out. Sigma 2s2, sigma star 2s2, they cancel each other out. Now you have 2 pi orbitals that are fully filled, pi 2p x2 and pi 2p y2, which means you have 2 pi bonds and no sigma bonds that are holding the molecule together. Very interesting molecule, right? So yeah, even here, if I want to calculate bond order, what will I write? I can see how many star based electrons. I can see 2 here, I can see 2 more here, right? And in all there are 12 electrons, right? So if 4 of them are anti-bonding, obviously 8 of them has to be bonding. So half of 8, half of 4, 8, half of 4. So half of 8 is how much? 4. Half of 4 is 2. So 4 minus 2 is 2. So C double bond, C is what we have. Interesting. 2 pi bonds, no sigma bonds, right? Yeah, so this is also going to exist basically. Now O2, 16 electrons, greater than 14 electrons, 1 to 2, 1, right? So sigma 1s2, sigma star 1s2, sigma 2s2. This is same for everybody. Then you have your 1, 2, 1, right? Of course, that 1 sigma star 2pz does not have any electrons, so I have not written. So sigma 1 is sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1. Basically, Hund's rule of maximum multiplicity works even here. So as far as pi star, see, by the time I reach till here, 1, 2, 4, I mean, how many orbitals are there? 1, 2, 3, 4, 5, 6, 7. So 7 into 2, 14 electrons are already filled. 2 more electrons are to be filled now, right? So after that, if I'm looking at pi star, they are degenerate. They have same energy, right? So Hund's rule of maximum multiplicity works here. I can't put 2 electrons into pi star 2px. I'll have to put pi star 2px1, pi star 2py1. But yeah, that doesn't affect our bond order calculation. It's just a side topic I'm discussing. That's all. So if I look at the anti-bonding electrons, I can see 2 here, I can see 2 here, and I can see 2 more here. So out of 16, 6 are anti-bonding electrons. So obviously 10 of them are going to be bonding electrons. So half of 10 minus half of 6, right? Don't worry about this, just because the boxes are there like this, I'm writing like this, you obviously will write like this only, right? So half of 10 minus 6 or half of 4, which is 2, right? So this is 5 minus 3 equal to 2. Of course, O double bond O, we already knew this as well. So yeah, this is your oxygen molecule, even that does exist. Last what we have is He2, which is obviously going to be our answer. Total electrons is 4, 2 into 2, and you're going to get sigma 1s2, sigma star 1s2, it's over also. And if I look at the bonding electrons, it is 2, and the bonding electrons is also 2. So this is half of 2 minus half of 2, which means it is 1 minus 1, which is 0, which means that He2 molecule, if I had to make it, its bond order will be 0, which means that such a molecule cannot exist, right? So whenever, I told you before also, whenever you see that bond order is turning out to be 0 or negative, you can say that that molecule will not exist. So identify the molecule which does not exist. It's obviously our D option, He2. Okay, so let's go to the next question now. Let's read the question. It says, identify the correct statements from the following. So some statements are given. We have to identify the correct statement. Let's read the statements. A says carbon dioxide gas is used as a refrigerant for ice cream and frozen food. B says the structure of C60, carbon 60, right, allotropic forms. Buckminster Fullerene or buckyball as you call it. C60 contains 12 6-membered rings and 25 membered rings. This is what is given to us: 12 6-membered rings and 25 membered rings. Next, let's read the C. C says ZSM5, right? So zeolite, right? So yeah, ZSM5 type of zeolite is used to convert alcohol into gasoline. This is what it says. And D says carbon monoxide is a colorless and odorless gas, right? So we have to identify the correct statements from the following. So let's so as far as the correct statements are concerned, and then we have to identify, so A and C are correct, or B and C were correct, or C and D were correct, or A, B, C were correct. We have to identify, right? So there are more than one correct statements here. Let's see. So one by one, let's look at the option. See, carbon dioxide in gas phase is not a refrigerant. We use dry ice, right? I'm not very sure that you might have seen this. The first time I saw dry ice was when I was in IIT, but so dry ice is something that is used as a refrigerant. You can keep your ice creams and all in it within the package, obviously, to allow it to remain cooler for longer. But the question said carbon dioxide gas, right? So carbon dioxide gas is not a refrigerant. Carbon dioxide in its solid form, in its dry ice form, is a refrigerant. So that is a tricky question. Right. Next was about C60. It said that it has 20 5-membered rings and 12 6-membered rings is what was said, right? So as far as C60 is concerned, it is one of the forms in which carbon exists, right? So of course, how do you make it? Carbon nanotubes and all of these have this very specific conditions under which they are formed and all. But yeah, as far as C60 is concerned, what is C60? Your Buckminster Fullerene that is there. It has these 5-member and 6-member rings. It's like a football, right? It's very much like a football, C60. Other Buckminster Fullerenes are also there. C60 is pretty famous, buckyball, and it's like a soccer ball, as I was telling you. One thing you have to remember is that these 5-membered rings are not supposed to touch each other, right? 5-member rings are only going to touch 6-member rings. 6-member rings can attach to itself. It can attach to 5-member rings as well. So as far as your C60 is concerned, you can remember that it has in all 12 5-member rings. Exact other way around, 12 5-member rings and 20 6-member rings, right? The 6-member rings can touch 5-member rings as well as 6-member rings. 5-member rings only touch each other, right? Only touch 6-member. So each 5-member ring, basically, you can think of it like this. So each 5-member ring is going to be a part of your 6-member rings. So 6-member rings can touch each other as well, but 5-member rings cannot touch each other, right? So if you have a 5-member ring like this, right? So 1, 2, like this. So around a 5-member ring, you will have these five obviously 6-member rings. 6-member rings can touch each other, and also 5-member rings. There are 12 such 5-member rings and 20 such 6-member rings that form your what you call as your so 20 6-member rings that are there and 12 5-member rings that are there. This forms what you call as your buckyball C60, right? So so a 6-member ring is fused with either a 6 or 5-member rings, and 5-member rings can only fuse with 6-member rings. So 5-member rings won't touch each other, basically. That is the idea, right? So this is Fullerene, right? So so you can understand that it was a wrong statement. Do you see how it's a tricky question? That 12 and 20 some people might be remembering, but is it 12 5-member ring or 12 6-member ring? That is what you have to remember as well, right? All the carbon atoms are like in graphite. All of them are sp2 hybridized. All carbon atoms are attached to 3 other carbon atoms, and there will be 3 sigma bonds and 1 pi bond obviously per carbon atom. So these are all something you have to remember, right? All carbon atoms are sp2 hybridized. Each carbon atom forms 3 sigma bonds with the other carbon atoms, 3 other carbon atoms, and 1 pi bond. right? Next was about your zeolite ZSM5, right? So zeolite ZSM5 is a very specific commercially made mobile company made this, right? So zeolite Socony mobile 5 is what you call as your ZSM5 zeolites. What are these? Zeolites are basically aluminosilicates, right? Aluminosilicates, the idea is that these have very specific porous kind of thing, right? So these are like mostly used as catalysts and all. These are heterogeneous catalysts. They are very effective because of their porous. You understand, I hope, what you mean by porous, right? So if you have something like your pumice stone, right, where there are like, because of the fact that they have specifically this ZSM5 is what you call as your pentacyl family. Pentacyls have like these 8 5-member rings that are, you know, connected. Okay, how if I want to draw the exact structure, that would be really weird. 1 2 3 4 1 2 3 4, right? So there are these 8 5-member rings that are there, and then there are these oxygen bridging bonds that are there through oxygen, right? So weird. Basically, the thing is that they have silicates. I'm sure when you studied about silicates, change silicates, closed ring silicates, and all of these, SiO4, right, 2- kind of. So aluminosilicates, the whole class of aluminosilicates is what you call as zeolites. They have this unique property that there are these holes that are there because of the crystalline structure, because of the way they are connected to each other. There are these specific holes that are there that you can think of within a zeolite crystal structure, and they help a lot in like catalysis, right? So there are these specific zeolites that can help you in achieving some particular result, like, you know, conversion from one isomer to other. There are zeolites that perform very different tasks, right? So zeolites find a wide range of application at a lot of places. One of the applications is what was written about in this question, that too specifically a commercial zeolite that is patented by Mobile Group. I'm sure you have heard of this, right? So Mobile zeolite Socony Mobile 5 is the full form of ZSM5. This is specifically used to convert methanol to gasoline, methanol to octane, right? So ZSM5 is a zeolite that is used to convert alcohols directly into gasoline. This is true, right? So again, there is no specific reaction and all that you can write here because it's a very different complex process that is going on, right? And last option was about carbon monoxide. It said that it's a colorless, odorless gas. Yes, in part 1 also we had seen carbon monoxide. The very reason why it is extremely dangerous is because it is colorless, odorless. You will not even realize that you have consumed a lot, you have inhaled a lot, and that has displaced all your oxygen, right? Oxyhemoglobin, and converted into carboxyhemoglobin. So yeah, that is why carbon monoxide is extremely dangerous. And let's look at the options once again, right? So we had to identify the correct statements, right? So so if you look at these, what do you see? As far as carbon dioxide is concerned, is it used as a refrigerant in gas phase? No. In solid phase, in dry phase, yes. C60 contains 12 6-carbon rings and 25 carbon rings? No. 12 5-member rings, less number will be the 5-member rings and more number will be the 6-member rings. So 20 6-member rings and 12 5-member rings. ZSM5 converts your alcohol, methanol, into gasoline and so on. Carbon monoxide is colorless and odorless. So I can see C and D to be true, right? So A and B are both wrong, right? So looking at the options, we can see that C option, which says C and D only, is the correct answer to our question. Okay, let's move forward. Let's look at the next question, right? Okay, so this is a very simple question here. Urea reacts with water to form A, which will decompose to form B. B, when passed through Cu2 plus aqueous, deep blue color solution C is formed. What is the formula of C from the following? Simple question here. Urea on reaction with water. I'm pretty sure that. Okay, let's put the options. Let's go forward. Looking at the options, I'm pretty sure you already can guess what is the answer. But yeah, what is happening? NH2, CONH2. First, when it is reacted with water, what do you get? I'm pretty sure that you have seen this before. You write it like this: NH2CONH2. NH2. It's a wrong way to write it, but yeah, this works for us, right? So we say that, okay, we will be getting NH3, NH3 and CO2, right? So NH2CO, NH2 plus H2O gives us 2NH4OH plus CO2, right? So we are getting 2 ammonium hydroxide. I mean, obviously it is not balanced. I should not be because I mean H2O liquid will have to be more, right? So with 1 H2 you would have got 2 ammonia. You need 2 ammonium hydroxide. You need 2 more. So 3 H2 would have been the one. But yeah, whatever. We are not looking at balancing. First, urea, when it is treated with water, when it is reacted with water, you get ammonium hydroxide and carbon dioxide is evolved, right? So ammonium hydroxide is the A that they are talking about. This, when it decomposes, gives B. What is that B? That B is ammonia, right? So ammonium hydroxide on decomposition, because it's not a very stable, right? So on heating, what you're going to get is ammonia gas and H2O, right? And after that, if you pass this ammonia gas into copper sulfate solution, to Cu2 plus solution, right? Cu2 plus aqueous solution, we know complex formation will take place. Tetramine copper 2 complex will be formed, right? So tetramine copper 2 complex is what we are getting, which has a deep blue color solution. And of course, what was asked was, what is this C? So this is exactly our C, which is the complex tetramine copper 2. Obviously, let's see. So yeah, the question was, yeah, so what was C was the question. Looking at the options, we can see that A is the correct answer. Tetramine copper 2 plus complex iron is our answer. So final answer is A option. Okay, so we saw all the questions from Inorganic Chemistry in our 2 sessions, and I hope you had fun going through all of these questions. I hope you realize that Inorganic Chemistry is not entirely about by-hearting things. There are ways in which you can understand them as well. Most of the things are just thrown at you as exceptions, and many times it's very difficult to go into details and explain. That is why many teachers would just ask you to by heart. That is the reason why Inorganic Chemistry, a lot of students feel that it's just something that is without logic. But I hope through the 2 sessions that we had, you understood that there is like a lot behind what is going on behind the scenes. There are like very subjective discussions around each question. The interaction individually between different elements and different complexes and all of these things is not a straightforward thing, right? There is no single rule that you can make or a single periodic table where you could exactly see repeating patterns and repeating reaction behaviors and all. That wasn't possible. All of these elements have their own differences, in effective nuclear attraction, size, ionization energy, electron affinity, hydration energy, lattice energy. There are these multiple factors that decide the overall reaction ability and what we eventually end up seeing in a real world scenario, right? But yeah, nonetheless, most of the questions we try to break down the question to see the exact logic behind them. We try to understand the concepts involved rather than just solving the question. I hope you had fun. This is all from BYJU'S. Best of luck. This is Abhilash saying goodbye. Take care.